Right. I'd like to acknowledge my co-authors or co-presenters. Frances Salisbury was a PhD student of mine. She graduated earlier this year, and she has been producing the model that I'm going to be talking about. And Aaron, everybody knows, he has been giving us great assistance in the development of this model. So just yesterday there was a lot of discussion about models and modeling. A lot of people were talking about it. And I just wanted to clarify the difference between empirical and mechanistic models. The empirical models are those types of equations that are fitted to data that are collected versus mechanistic models which explore the underlying mechanisms involved in the process. And the benefits of mechanistic models over empirical models is that they identify gaps in our knowledge of a subject, and we can then identify innovative and useful topics for research. And for supervisors of a lot of students, it's a wonderful means of identifying work that can be done by the students for their postgraduate studies, as I have discovered over the years. Because you can identify these topics for research, you can design experiments that target the critical questions that are raised by the identifying these gaps in our knowledge. And that, in turn, provides us a better understanding of the underlying mechanisms of the subject. And then once you have developed this mechanistic model, you can then integrate that with a feed formulation program and enterprise optimization to improve the margins for feed intake and product value on the farm. And I'll go into that a little bit more as I go along. So one of the other differences then between empirical and mechanistic modeling is the applications for empirical modeling are limited to the conditions under which you design the experiment and derive the equation, whereas mechanistic models can be applied to new scenarios. So you don't have to do the experiments in order to make use of the models to answer the questions. So the mechanistic modeling approach that we've been using have proved really invaluable in improving the precision and economic optimization of amino acid and energy nutrition. So we've concentrated up to now on amino acids and energy, and we make use of these models to answer what-if questions. So the what-if questions about the genotype, the feed, and the environment. So for example, you can find differences between males and females, different breeds, different environments, and different lysine levels, different stocking densities. Anything that is considered in the model, you can make use of to answer what-if questions. And then by integrating that with the feed formulation program, you can determine how the feeds should be fed to the birds to maximize or minimize an objective function. Now, 2 years ago at a poultry science meeting here in the States, I presented this slide, and I think it's worthwhile having a look at it once again to give you an idea of how you can choose different objective functions and how the model, the optimization model, alters the feeding program, the feeds in the program, in order to maximize or minimize the different objective functions. So on the left-hand side, the base is making use of the Aviagen lysine requirements of 2 years ago. They have changed these, but those were the starter, grower, finisher lysine requirements that they had recommended, and the model produced the results that you see under what we the base column. Now, if you want to maximize margin over feed cost, which is a very sensible thing to do, you can achieve that by, as you can see from there, I can't, but as you can see from there, you can increase the margin over feed cost considerably by altering the lysine content in the starter and the grower and the finisher. So going higher in the starter, lower in the finisher, you get a much higher margin over feed cost. Alternatively, you could try to minimize feed conversion ratio, which is not a sensible thing to do. You can achieve that, an increase of 3 points in feed conversion by going to higher levels of lysine in the starter, grower, and finisher. But have a look at what happens to the margin over feed cost when you do that. It goes down considerably. In the Netherlands, they like to minimize nitrogen excretions, and you can achieve that using the optimizer, and it goes down from 10 down to 8.7 grams per bird, and you can achieve that by going to lower levels of lysine in the starter and grower. In the finisher, it's the same level as when you maximize margin over feed cost. So you can choose any one of the variables that is simulated in the model to use, and you can either minimize or maximize that. And in the future, then maybe we can minimize phosphorus excretion, for example, or maximize bone strength by using mechanistic models. So the mechanistic models that we have been developing provide a framework for the modeling of calcium and phosphorus in the broiler. And the question is, why would you want to model calcium and phosphorus? And I have a number of points there in different categories: biological, environmental, and economic reasons why you would want to model calcium and phosphorus. For example, there's this very complex interaction between the minerals, and as soon as you have complex interactions, it's worthwhile modeling them to try and understand the interactions. Or you might want to reduce phosphorus pollution, or reduce the cost of phosphorus in the feed. So there are good reasons why we want to model calcium and phosphorus. The interaction between calcium, phosphorus, phytate, and phytase are highly complex. And because of that complexity, it's worthwhile thinking in terms of a modeling approach. And I've given a number of pointers to showing how the interaction, where the interactions take place. And I will, in my presentation from now on, I'll concentrate on 3 of those. The potential growth rate of the broiler, the effect of shortages or excesses of calcium and phosphorus on growth, and the effect of excess calcium on phosphorus digestion. Those are just 3 that I can discuss in the presentation here. So the minimum amount of information that is needed when modeling a mineral model is that you need to know what the potential growth of calcium and phosphorus is in the body under ideal and non-ideal conditions. You have to quantify those in order to describe what the bird is trying to achieve, so that you can work out what the bird needs by way of calcium and phosphorus. You need to know the availability and digestibility of nutrients ingested by the bird, understand these and how they meet the requirements for maintenance and growth. And you need to consider the mechanisms that regulate feed intake and mineral absorption in order to understand how much to feed and what the consequences are of feeding different levels. And you need to separate out the soft tissue and the bone, and the amounts of calcium and phosphorus in the soft tissue and the bone, so that different priorities can be given to these tissues when the levels of calcium and phosphorus in the feed are below what the requirements are. The advantage of using the existing model and adding this mineral module to it is that most of the work has been done as far as the growth and food intake prediction of the bird is concerned, but based on amino acids and energy. So the potential protein growth we predict very accurately. The environmental conditions that influence the growth and the food intake are considered, and we predict both the desired feed intake and the actual feed intake, which then can be modified to account for the levels of calcium and phosphorus in the feed. When we got to start modeling this, we found that there was a dearth of information available to produce a calcium and phosphorus model. There are hundreds of publications on calcium and phosphorus, most of them in recent times to do with phytate, and amazingly, phytate works, but it doesn't help. Those kind of papers don't help when you get to model calcium and phosphorus in the bird. Some of the questions that we wanted to answer was, what's the potential rate of calcium and phosphorus deposition in broilers in relation to the body protein growth? And as I will discuss in a moment, out of hundreds and hundreds of publications on calcium and phosphorus, there were just two that addressed this issue. And one of those we had to really delve very deeply to understand what the protein content was. We need to know what the proportion, the potential proportion of calcium and phosphorus in the soft tissue versus the bones is, and by how much this can vary from the ideal. There was one publication many years ago on this, and all publications thereafter have used that publication, the results of that publication, without anybody ever doing any further work on that particular subject. And then, to what extent will broilers compensate for low calcium or phosphorus in the feed by consuming more? Do they do this? There's no information about that in the literature. We had to try and answer the question as to why intake is reduced when high calcium is fed or when very low phosphorus is fed. So these are issues that we needed to consider, and we found very, very little information in the literature about them. So to take the first part, the first question that we wanted to address, how much calcium and phosphorus is deposited in the body? What is the potential deposition of calcium and phosphorus? So the way we go about doing this for all physical and chemical components of the body is that we describe the growth, the potential growth of body protein using a Gompertz growth curve that you can see there, and the derivative of that is the change in body protein content over time. And we then make use of allometry. So you take the natural logs of body protein and the components, the chemical or physical components, and that, by taking the logs of each, you get the straight lines. And you can see there that the body water has a slope less than 1, which means that as the birds grow, the rate of deposition of water slows down in relation to the rate of deposition of protein. Body lipid is exactly the opposite. The lipid content increases in relation to body protein, and body ash is isometric. It grows at the same rate as body protein. So we were fortunate in being able to make use of some data that was collected at the University of Arkansas on the Cobb 700 bird, and we analyzed the body protein, the ash, the calcium, and the phosphorus content of these birds as they grew to 15 weeks of age. And we fitted allometric relationships with body protein, and in all cases, as you can see, these relationships fitted very well. The ash content, the slope was very close to 1, as we predicted. The slope of calcium is greater than 1, so it looks as though they deposit more calcium as they grow. And phosphorus content was about the same as ash, so almost isometric. When we looked at the results in a different way, we looked at the phosphorus content as a proportion of body protein, and we plotted that against the age of the bird. The allometric model that we had developed in the previous slide fitted the data pretty well, except for 2 outliers. And those 2 outliers were real outliers compared with the rest of the data. And so we then had to troll through the previous literature, and we found these 2 papers that had addressed this, or that had given data on phosphorus and calcium and protein, and we found that they had also discovered that in this early period, up to about 3 weeks of age, the mineralization is much higher than would be expected on the basis of an allometric relationship. The one paper is by Justina Caldas. She didn't produce protein. She used DEXA and produced lean. So we had to correct for the water content of the lean and the feathers on the body. So it's not absolutely ideal, but nevertheless, those values, the red squares up there, show that the mineralization in that first period is very high. And the other is Anke Diekmann, who is Markus Rodeholzko's student in Germany. So it looks as though in that first period there's a very high rate of mineralization, which then comes back to the level at about 3 weeks of age. And the same thing applies to calcium. There's a much higher rate of mineralization there that takes place early on. We don't understand about this. This is the first time that this has actually been spotted, really, and we have to try and figure out how to deal with this. Is it real? Is it real? Do we need to make changes in the way that we feed the birds in order to get them to mineralize at that rate early on? So this is an issue that's been raised by looking at the model. The second issue that we're looking at is the extent to which calcium phosphorus influence food intake and growth. With our broader growth model, we believe that the birds will eat to try and satisfy a requirement for the first limiting nutrient in the feed, and if that's an amino acid, they would overconsume energy and become fat. And we wondered if that might be the case with calcium and phosphorus as well. We wanted to find out if they if the food intake would be adjusted according to the level of calcium and phosphorus in the feed, and then whether we could predict that in the future. We did a trial, the results of which are here in this graph, and you can see what I've plotted here. We had 6 levels of calcium and a range of non-phytate phosphorus levels on the x-axis, and I've plotted the growth rate as a proportion of the maximum. So the maximum growth rate is on the right-hand side at the top, the calcium level of about 6 to 8 grams per kilogram, and non-phytate phosphorus of about 5 grams per kilogram. That's where you would get the maximum growth rate, and if you reduce the phosphorus level, growth rate is reduced. If you increase the calcium level, you can see you get a tremendous drop in growth as the calcium level goes up. So there's this huge interaction between calcium and phosphorus in growth and in food intake here. The food intake it shows the same principle as at the very low non-phytate phosphorus level. As you increase the calcium content, food intake decreases. Now my Brazilian friend, Matthias, has a model. He's published a model, and he believes that food intake is the primary responder to that interaction. We believe that the adverse mineral content constrains growth, and that results in a lower feed intake. So it's a question of chicken and egg as to which of us is correct. But the way in which we go about modeling that is that we reduce the rate of maturing parameter in the compost equation, and by reducing that, it reduces the potential to grow, and that in turn means the bird is going to grow more slowly and doesn't need as much food, so the food intake decreases. And we make that same strategy to model disease infections and vaccine reactions in the model. The third issue is predicting calcium and phosphorus digestibility. The most common approach, I think, is that digestibility values are included for each ingredient in the feed formulation matrix, and that really assumes that the digestibilities are additive, but that's valid only when the ingredient digestibilities are measured in feeds with similar calcium, phosphorus, and phytate levels, and the complete feed also has the same levels of calcium, non-phytate, phosphorus, and phytase. Where the levels vary, and they do very often, an alternative approach has to be used because of the interaction between calcium and phosphorus that interferes with these assumed digestibility values. And the reason for this interaction is that calcium has a negative effect on phosphorus digestibility. I'm sure everybody in the audience knows this. It's a result of this its ability to bind and precipitate both phytate and, to a lesser extent, non-phytate phosphorus in the gastrointestinal tract. And so that reduces the availability of both calcium and phosphorus, and that leads to a reduction in growth. And that I showed in the graph earlier. But in our model, we can model we can illustrate the effects of any of these issues. I'm hoping that this will work. It's not going to. Oh, it's going. You can see how we model the effect of increasing calcium levels on growth in the model itself. So we have three different methods of including the digestibility values in the model. One is to make use of a digestibility model for both calcium and for phosphorus. We can enter the values manually. This is for the complete feed. Or we can make use of the digestibility values that have been input for each of the ingredients in the feed formulation. And by making use of the digestibility model, you can see at the bottom the effective value, the effective digestibility value that is calculated. Now, we make use of Matthias Ries's digestibility model for phosphorus. I believe that was based on a meta-analysis, and we don't have anything better at the moment, although we are working hard on getting a better model. The problem with this one, as reported by the authors of that publication, is that it's not very robust. This empirical model only works within a very narrow range. And for example, at very low calcium levels, the digestible phosphorus is greater than the total phosphorus when phytate is added. So there is a need to improve this empirical model to calculate the digestibility of phosphorus. So the planned current and future research, we want to describe the potential calcium and phosphorus deposition in different breeds, the breeds that are made use of in the commercial broiler operations these days. We want to gain a better understanding of this increased mineralization before 21 days of age. It's really important, I think, to understand why that is and whether that will alter the requirement for calcium and phosphorus in that period. And we want to improve the empirical model describing phosphorus digestibility, especially when phytase is added to that. And we want to gather more information about the relationship between calcium, phosphorus, and body protein. And anybody who's doing experiments should really, with calcium and phosphorus, should really analyze the body protein at the end of the experiment to help us along with our model. It would be very valuable to have that information. Now, we've actually done a lot of these experiments already, and we're having a hold-up with the analysis of the minerals at the moment. But we've been making use of choice feeding and mixture experiments, amongst others, to address these issues. So we are addressing them as fast as we can, and the model will benefit from the results of those experiments in the future. Right, so I have 2 slides left, and these are to do with biomarkers and modeling, and it's really an introduction to what Aaron is going to be talking about later. DSM Firmenich has, they've been very, they've made use of our broiler growth model, and they've supported the development of this mineral model. And they have a product called Verax, which Aaron will talk about, that has has a very interesting, they've collected interesting, useful data using this system on plasma calcium and phosphorus, and how that relates to skeletal abnormalities or calcium and phosphorus supply. And that's seen as being very helpful in optimizing dietary calcium and phosphorus levels in the feed and phytase dosing, etc. So that's a different tool that's available for customers to monitor the bird performance, bird health, nutritional status, and optimize dietary calcium and phosphorus nutrition. And the way that it's done is they collect samples, blood samples from birds in the flock. They analyze those blood samples and make recommendations as to how the calcium and phosphorus levels can be adjusted. And then the cycle is continued until such time as the birds are performing perfectly. And that's exactly the same system as we make use of with our optimization. The top circle would be a feed formulation program where a feed is formulated. It's taken through to the broiler growth model that simulates the effects of using those feeds. The optimizer takes the results and decides in which direction it should go in order to maximize or minimize the objective function. The feed is then altered. The broiler model again simulates the results, and that cycle continues until such time as the objective function is either maximized or minimized. So the approach used in these two systems is identical. And that's the way of improving the optimization of calcium phosphorus nutrition in broilers. So that's all I have to say, but I'll leave you with that quote from one of my mentors, one of the greatest poultry scientists, I think, that's been around. And with that, I thank you.